The remainder estimation theorem. So looking at the Lagrange form of the error term, so it's going to be our n plus 1 term. So we have it here, our Rn of x is going to be the n plus 1 derivative over at some point b. And again, we know that we don't know exactly what b is, but we know the bounds of b. It's between the center and the x value we're estimating, divided by n plus 1 factorial times x minus c to the power n plus 1. So we know that we want to maximize the error. So we want to know what's the worst case scenario here. So we can maximize the error by finding some constant m, where m is going to be the maximum value of the n plus 1 derivative. So we're going to call that point k, and that point k is going to give us the worst case scenario for that error. So b is going to be the best case scenario. Okay, b is going to give us the exact remainder, but k is going to maximize our error, and that is going to give us our error term. So we know that our error can't be more than so much above or below the point that we estimate. And again, k is going to be bounded between c and x. So we're going to then, once we calculate m, we can then calculate the remainder, which is the max error. So this Rn of x is in green is going to rep with the maximum error term is going to be the max error of our approximation. So what does this look like? So let's take a look at when we cut off the Taylor polynomial at n equals 3. So firstly, we're going to get our derivatives. So we have the derivative, we're going to estimate e of 0.5. So we're going to differentiate e to the x. That just becomes e to the x, e to the x, e to the x, e to the x, and we're going to use the fourth term for our error term. That's also going to be e to the x. So this represents our error term. So our when we evaluate it at the center, it's just going to be 1, 1, 1, 1, and then our coefficient is going to be 1 over 0 factorial, which is 1, 1 over 1 factorial, which is 1, 1 over 2 factorial, which is 1 over 2, and 1 over 3 factorial, which is 1 over 6. Okay, and this will be 1 over 4 factorial, which is 1 over 24. Okay, so then let's look at our approximation. So e to the x, so e to the 0.5 is going to be equal to, our first term is just going to be 1 plus 1 times x, which is 0.5, plus 1/2 times 0.5 squared, plus, let's move this down a little bit, 1 over 6 times 0.5 to the power of 3 plus the remainder. Okay, so we have our approximation here. We're going to say that our approximation, this is approximately equal to, when we work this out, we're going to end up with 1.645833. Okay, if we compare that to the actual value, so if I actually work out e to the 0.5 on our calculator, that works out to be 1.6487 ... Okay, and we can see that the error then we have at this term here, we can see that it's doesn't quite match. So our error is going to be in our third decimal place. Okay, so that's our Taylor approximation. Let's work out the error. So we're going to make error bounds because we can't actually find b, but to find the actual value of R3 of x, but we know that b exists somewhere between 0 and 0.5. And what we're going to do is we're going to maximize that error value. So we know that the maximum value of m is going to be when b is going to be the greatest. Okay, so if I plug in 0, I get 1. If I plug in 0.5, I'm going to get a number bigger than 1. And it's strictly increasing graph, so we know that the maximum error must occur when we plug in 0.5. So we're just going to use 3 as an estimate for E and use that as our value. If we don't know exact, since E is a transcendental number and that it is irrational, we can't actually get the exact value of E. We're just going to use 3, and that's going to give us an even greater error bound, so we can be even more confident in our estimation or error estimation. So then our m value, we know that it's going to be less than or equal to, we're just going to say e to the 3, or sorry, e to the 0.5. And we know that that's going to be even less than 3 to the 0.5, which we're going to use as 1.732. So then our error, our max error, we know our max error must be less than or equal to the m value, which we're going to use as 1.732, divided by 4 factorial times by 0.5 minus 0 to the power of 4. So I'm using this expression here to calculate the maximum amount of error we can expect. So working this out, we know that this is going to be less than or equal to 0.0045. So in our third decimal place, we know that we can expect a plus minus 0.45 from our estimated value here was 0.645. Okay, so we know that our maximum, the worst case scenario would be it must be less than, okay, and working that out is going to be, we know that the actual value must be less than or equal to, when we add 0.45 to that, we get 1.645 plus 0.0045, and we know that it's got to be less than 1.6503, and we know it's got to be bigger than that same amount, but our Taylor approximation of 1.6458 minus 0.0045, or 1.6413. Okay, so the actual value is going to be bounded between those two values.